So tonight we're going to talk about week 5. We're in week 5, believe it or not, already. And before long, summer courses will be being pushed. They already started pushing them on social media already. I have a boot camp in May that I teach, an iOS boot camp. It's 4 Saturdays in a row, and it's Web 290 or CIS 290, and it's summer session 1. If you're interested in mobile app development, or you maybe want to just try it out, it's only 4 weeks. It's 4 credit hours for the 4 weeks. I take it back, 3 credit hours for the 4 weeks, and no textbook needed. You don't need an iPhone or iPad. I provide the iPads for the 4 weeks. We will be creating apps in simulation mode on a simulator using Swift programming language. And you'll be creating a map app. You'll be creating a game app, a shooter game app, a notepad type of app, and then a back-end database app. The back-end database app we're doing this time is a crime database app that gives live crime results, well, within 24 hours anyway. The last 24 hours of crime within whatever region you're at in the Rockford region. And so there's actually a database in Rockford's city website that we use to get the crime database. And so anyway, and a number of other classes. I think we have a 102 in summer session 1. And then summer session 2, we have a couple 102s, I believe, as well, which most of you probably already taken. So do recommend the iOS boot camp. It's a lot of fun. I do feed you, by the way. It's on a Saturday from 8:30 to noon, or 12:30, 8:30 to 12:30, 4 Saturdays in a row. It does start right after the final week, that Saturday right after our finals week. But it's going to be creeping up before too long. I think March something is the registration date opening for summer session 1. So this week 5, we're going to be going over, as always, some discussion here in a second in the chapter 4, which has review questions and quiz as always. The lab is a network LAN lab. You already have the handouts, which I'll kind of talk about what this is on the board, which corresponds with what you have on the handout. You will need to be, let me see here, 1, 2. I'll probably rearrange you guys to where you're at least in a row of at least 2 people, 3 preferably, but if we can do 2, we can do 2, it's fine. We have 9, so we actually do 3 rows of 3. It should work fine. So this is something you're doing all the time in networking, by the way, what we're going to do tonight. At the end of your rows, you might have noticed when you came in, there was, and maybe in the middle, hub we'll be using, showing you how to configure that, and Cat5 cables, straight cables. You'll be creating these here in a bit. Not tonight, but you'll be creating them this semester. And you'll learn how to hard connect, set up IP addresses, hard code your IP addresses in your TCPIP version 4. We'll walk you through that. And you'll share a folder on your computer once it's all set up, and you will write into each other's folder on each other's computer through the network once you've set it up. So it shows you how to set up a local area LAN, writing files, which you do all the time as well on a network. And so after tonight, if you've not yet done so, you will have set up and started learning how to set up a LAN. So we're going to go over TCPIP protocols tonight. And there's 2 protocols mainly, but there's other stuff we're going to talk about within that deals with the OSI model. Version 4 and version 6 are the 2 protocols mainly, or only actually in TCPIP. And we'll also talk briefly on DNS. So TCPIP basically stands for Transmission Control Protocol / Internet Protocol. The Transmission Control Protocol is the rules of the IP. If you remember the video a few weeks back, it talked about how the IP is kind of like the wild, wild west. There's no rules. It can just do whatever it wants, go wherever it wants, which is the case. It's connectionless. TCPIP or TCP is the rules around the IP that determines source destination, routers it's going to hit, things of that nature. How long it's going to take, how many hops it can take, the time to live that we talked about last week in ping. So there's some sub-protocols within this suite, TCPIP, IP, UDP, and ARP. In my 130 class I teach next semester, the network security class, we deal heavily into ARP poisoning, where hackers use to poison a ARP table on a network to do a man-in-the-middle attack, to where everybody in the company or in the Starbucks is going through a hacker's machine, unbeknownst to them, and getting all the data that those users are doing, whether it be internet, typing in their computer, a website, a password, sucking all passwords from devices that are connected. Pretty scary stuff, all with ARP poisoning. And ARP poisoning is pretty easy to do if you know what you're doing, and it doesn't take long to set it up. It was developed, this TCPIP was developed by the Department of Defense, called ARPANET, in the 60s. It was the internet precursor, or the web precursor. It was mainly designed for military and universities to communicate securely. That's what it was first originated for. Not downloading pictures of cats or cat videos. Believe it or not, it was for secure communication only, no fun and games. Popularity of TCPIP became very popular because it was very low cost to integrate into hardware. It communicated amongst all different platforms. Dissimilar platforms would be like Apple, Windows, Linux, no problem. Open in nature, meaning that it can be programmed, integrated into any type of device, both open and closed both. It's routable, meaning it can route different segments of the LAN. I think I talked a little bit last week about at Rock Valley when we first had a flat network. We merged eventually to a tiered network where we had data and voice on a tiered network or on a subnet segment network. It's flexible because it runs on a combination of network operating systems and also different media. So wired, wireless, Cat5, fiber. Disadvantage, it does require more configuration, but really not too much. If you know what you're needing a network to do, and you already know your IP range and your subnet, which we'll talk about a little bit tonight, I don't really see that as a disadvantage. It's just a tool that you have to configure, and once you learn how to configure, it's not real hard to remember, especially if you do it every day, which you'll be doing if you're going into networking or any branch of networking. You'll be a lot into TCP/IP, a lot in all the protocols. So the sub-protocols operates, and the protocols both for TCP/IP operates in the transport and network layers of the OSI model. And the OSI model, remember, is a theoretical model. It's not a real hardware or software, but it's representative of all levels of networking and communication. Some of them overlap each other. Some of them, overlap one above, one below. But they all communicate, and it's for the purpose of troubleshooting, for the purposes of training, for the purposes of testing, basic services and the protocols and other layers as well. The most significant protocol in the TCP/IP is the TCP, which is the rules, and the IP, which it's governing the data and where it's coming from, where it's going. It makes sure basically the IP that it gets where it's supposed to go and all the data gets delivered. That's what the TCP does. So the transport layer protocol provides reliable data services. It relies what's called checksums and connection-oriented sub-protocols. We talked a little bit about handshaking back in the days of dial-up. We still have it today, you just don't hear it. That would be in this establishing connection before transmitting. And that connection would be not only that you can see the IP address and you ping it, but you authenticate it as well a lot of times. Like when you log into, I don't know, anything, your bank, social media, Google, your email, RVC Eagle. It's all handshaking going on during the time before you're connected to make sure you are who you say you are. Then it gives you the rights you need. Then you're there for your data flow. It has sequencing and checksums. We talked about the cabooses, remember, how large data bits are broken up into little chunks into cabooses and then put back together on the other end and resequenced back. Flow control, data does not have flood node, meaning that in flow control for the transport layer protocol, it's basically seeing where things are going, but it's really not controlling anything. It's just seeing where it's going, that it sees a router out there, it sees a switch, it knows at any moment's notice what's around it. The TCP segment format is encapsulated by the IP datagram, and it becomes what's called the IP data, or the payload of the packet. So here's a screenshot of a TCP segment. I'll circle a couple things that's important. This is actually for version 4, TCPIP version 4. Data packet on this will be the very bottom one, the data. That's the payload of the important part of what's being sent. But you'll notice also source port, destination port. Sequencing number is a random number given for the sequencing number of that data. Acknowledgement is a number of acknowledgement. Acknowledgement you're connected. Acknowledgement you're authenticated. Acknowledgement that you're disconnected. Just a couple of acknowledgements. In this header row here, basically this is from ARPANET days, and some of this stuff with version 6 we don't even use anymore, and even in version 4 we don't. But it's still there. It has in there the length of the header, reserved little columns there. Those are flags that in modem days you'd actually have, each one of these would have a flag light on a modem. Now you don't have that. It's built into the operating system and into TCPIP. But you can tell by some of the acronyms: urgent, acknowledgement, finished, synchronized. Those are all handshaking things that are going on, connecting, disconnecting. The sliding window size is a static data port or data area of the segment. Checksum checks the data that it is not only from the source, but it's an exact size from the source, total size of the packet, and the checksum number matches the checksum number received, matches the checksum number sent. Urgent pointer, there are some appliances and Cisco and routers where you can give certain IP addresses or ranges priority, like servers would have priority over any client in the network, over making sure they get bandwidth and they get information sent quickly. The options and padding are basically needed for other data types, other data file types. And the reason that was created was when ARPANET first created the TCP/IP, they really had no clue what file types or data types would be there. So that's why it was named options and padding for that purpose. Really, with version 4 and version 6, both that we have today, this column isn't, or this row isn't used much either anymore. So here's a text version of what we just looked visually. I'll highlight a couple things because it gives a little bit more information. Source destination port, or source port's port 80 coming out from the computer. Destination port 1958. This would be like a server you're clicking a link on. That would be the port number. So an example, port 80 would be you, and 1958 would be the RVC Eagle server when you logged in tonight. There's a sequencing number, the acknowledgement number. Here just breaks it down, source, destination, sequencing, everything here I just circled above is now here in this area. The flags for handshaking, authentication, connection, disconnected. Then finally the segment size. This is actually the caboose part. Every caboose can only be 1,460 bytes per. So however large the data is, it's going to divide it evenly up to that 1,460 bytes and then resequence it once it is sent and received wherever it's sent at. So 3 segments establish connection, like computer A issues message to computer B, sends a segment. The send field, a random synchronized number is created. Computer B receives a message, sends back a segment, acknowledges it found that segment. Computer A sends a +1 to it to acknowledge it. The send field on computer B gives back a random number. Computer A responds, sends a segment back. Acknowledgement field, sequencing number +1. The send field, computer B, random number again. The FIN flag indicates transmission is ended, and that can be just not disconnected or logged off, just when you download a file, FIN happens. When you submit a file in Eagle or text or whatever, it happens. So anytime a transmission occurs of any type, FIN happens multiple times, not just at disconnection, but multiple times. So here we have a connection here, visual connection number 1, request for connection, send with acknowledgement, this number here. 2 responds, send acknowledgement with another random number, acknowledge number here. Notice on this number here, this 559, all it did was add 1 number to the 558, which was originally created here from the sending computer. Then 3, the established connection, acknowledges again that 937031559. That is again this number here, right there. And then this green, I'll point it to the red here, adds 1 to it. So that one's a 69 there, and the bottom one's a 70. So acknowledgement and receiving both adds 1 to it. That way they know it did get it, and it pings it back, I did get it. And that's actually why on pinging that we went over, how it can decrement every hop. Here's how it does it, because it uses that 1 increment every time. UDP, it's a user datagram protocol within the sub-protocols of TCPIP. It's in the transport layer of the OSI. It provides unreliable data delivery services, connectionless, basically meaning no rules on this one. No assurance that packets received in a correct sequence, no guarantee packets received at all, no error checking. It lacks sophistication, more efficient than TCP because there's no rules. Anything that has no rules is generally faster, but doesn't mean it's safer, doesn't mean it's going to get there. Useful situations, great volume of data transferred quickly, all right? Video and audio uses the UDP a lot because it needs large, if you've ever played with video or audio, a lot of data is being pushed through all the time. So streaming, anything streaming you've ever done on your phone, tablet, computer, uses UDP a lot for communication. Because really, there's no checks needed. It's just data being pushed. And it needs to be pushed now. If you put checks in there, it's going to slow it down, which causes the video to be choppy, the sound to be choppy, and that's not good. So you'll notice the packet on this, UDP is much smaller, the segment is, much smaller in content. You got a source port, destination port. The length of the packet, checksum, 2 data, that's it. The IP, Internet Protocol, falls on the network layer of the OSI. It shows how and where the data is delivered, includes the data source and destination. It enables TCPIP network or internetworking. It can traverse on more than one LAN segment. Like this building here can converse with CL1, CL2, Samuelson, PEC, Student Center, Maintenance Building. Multiple LANs connected one to the other. No problem there. Network layer data formed into packets called the IP datagram. Has an envelope. Each contains information for routers to know, okay, where does this packet come from? What IP address? Where's it going? And routers can move it around. So as you saw in the video, sometimes packets get dropped, they get lost, they get destroyed. IP packets, the router asks for that again and sends it until it's completed. So there's some redundancy, but on purpose, so data makes sure it gets there. It's unreliable by itself. It's connectionless protocol, IP is. No guarantee of delivery. It's used by higher level protocols. Ensures packets delivered to correct address. It does do that. Reliability component. It does have a header checksum that verifies routing information and the integrity of the IP header. Now this is important, especially when it talks about man in the middle I talked about earlier. If somebody does intercept a data packet and makes changes to it, it will be reflected here in the header checksum. And the IP will know that it's been changed. And it can give a flag, it can drop it, it can kill the connection altogether, which you might have seen before maybe. Especially if you've been in an area maybe, and you maybe didn't know this happened, but you've been on a certain access point, Wi-Fi access point, and there was maybe a rogue one out there you didn't know about that your computer connected to. It started getting connected to the internet. Maybe you're already doing something already, like downloading a file or on a website, maybe on a bank website. It can determine, especially on a banking website, what your security wrapping is, what your security connections are. And if the headers change in any way, shape, or form, it'll kick you off not only the bank website, but your computer then will kick you off of that SSID. It might take a while for you to reconnect. That happens all the time, by the way, because it's built-in safety that TCPIP has without any other software, without any antivirus, without any malware. It does it for us. Now, it's not perfect and it doesn't always work all the time, but it does work most of the time. So here's an IP packet. Top left version. The one mostly used today still is version 4, but we do have up to version 6. IHL differential services, total length of bit, identification, flags, fragment offset, time to live. You've heard this when we went to the ping. Protocol, header checksum. Protocol would be like HTTP, HTTPS as an example, FTP protocol, just to name a few. Maybe SMTP for send mail, POP protocol for receiving mail, source IP address, destination IP address, options, padding, and then the data. This is just flipping it in text version. Only thing I'll mention on this one is the source IP and the destination IP. ICMP, the Internet Control Message Protocol. This one is a network layer protocol. Reports on data delivery, success or failure. It announces transmission failures to the sender. Network congestion would be an example of causing failure. Data fails to reach destination. Either the computer is turned off, they lost connection, wire was crimped, hardware failure. Data was discarded, maybe the TTL expired. And remember we talked about ping. Ping gives us only so many TTLs up to 255. Generally it's going to be around 125, 130, 140, 150, somewhere around there. Once it reaches 0, it drops that packet, drops that connection. ICMP cannot correct errors. It does provide, though, critical network problem troubleshooting information. Internet Group Management Protocol, IGMP. It's on the network layer, manages multicasting, one node sending information to a defined group of nodes, similar to broadcast transmission, point to point. So satellite would use this as well. Point to multi-point. Uses internet teleconferencing, video conferencing, routers, network nodes. ARP, talked about this a little bit already. ARP is basically a table on the network, all right, that knows every IP address, every MAC address in your network, okay? It's built into the router, ARP tables are, and ARP tables also can be poisoned. And the built-in, once an ARP table is poisoned on a server through a router, you can do, redirect traffic to whatever machine that you want to once the table's been poisoned, ARP table's been poisoned. So basically an ARP table obtains host information like the MAC address of your computer, your mobile device, your laptop, your tablet, whatever. It creates a database, much like an Excel spreadsheet. It maps the MAC address to the IP, which every computer has, every server has, right? We talked about a few weeks back when we did the slide showing the NIC card having a unique MAC address, like a VIN number on a car. That is unique, but IP addresses can change, okay? But MAC addresses don't change. An ARP table can actually change MAC addresses, meaning if an ARP poisoning attack occurs, I can change the IP address or the MAC address of in the ARP table to be not the server. Say the server's address is a .1. I can now make the MAC address in the table not be the server's MAC address, but my MAC address. And when I do that, all traffic then goes through me. It sees me as the server, not the actual real server. So the ARP cache, basically, there is a command you can do and learn called clear cache, clear ARP cache, which will clear all ARP tables and reinitiate it and rebuild that table. Hackers will use that, by the way, after an attack. They'll do an ARP cache clear to wipe out any traces that they've been in that network doing anything, and it refreshes any logs and deletes any logs and any trace of any activity during that time that the hackers run the man-in-the-middle attack. And by the way, man-in-the-middle attacks are used predominantly in Wi-Fi hotspots like Starbucks, any free Wi-Fi hotspot in an area. It's used a lot where people connect to all the time. And the hackers will create an SSID the same as that area, but the way SSIDs work and Wi-Fi, your computers will glom on to the closest one to it. And so hackers will create a rogue access point. It can be created, by the way, from any device. I can create a rogue access point from my iPad Pro, my Mac Mini, even my laptop, desktop can be created. Ad hoc Wi-Fi access point very easily. But ARP tables, they do increase efficiency because you don't have to, if we didn't have the ARP table, every time people would log in every morning, the computers, the network server would have to build some temporary table of some type just for communication. So it would know who's who, right? I do it on the fly every time. ARP tables, generally, the cache part, unless it's cleared, stays static. What that means is, you might understand this, that most of us in school here, at your workplace, we have, and we'll talk about more this semester, DHCP, anybody heard of that before? Where your IP address is given, can be changed periodically. Meaning you don't hard code your IP address in your computer, you're just given one. And generally those DHCPs have a lease that they have like 24 hours, 48 hours. But a lot of times your IP address won't change for months, maybe not years in environments. And the reason it doesn't is if there's no real changes in your environment, that ARP table is going to stay the same. The cache in there is going to stay the same. And unless it's needed, it's not going to change. So because it's cached and because it's a database, it's easier to connect and faster to connect. Because when you log in, ARP table already knows, okay, this is your MAC address, this is your MAC address, this is your IP address, done. Don't have to build that over again. It's just much quicker, creates efficiency. Two types of entries in an ARP dynamic. Created when a client makes an ARP request that cannot be satisfied by data in ARP table. And static, where you can manually enter in using an ARP utility. Now with ARP utilities, you can, if you know what you're doing, you can actually poison an ARP table, or clean an ARP table, or edit an ARP table. And it's an ARP command from a Windows, Unix, or Linux prompt, like the ping command. And there's a number of options that you can learn on ARP table information and manipulating ARP table content. So here's an example of ARP in text format, example ARP table, what it looks like. So you got IP address, hardware address, and type. IP address is the IP address of the computers on your network. Hardware address is a MAC address of the computers and servers on your network. And type is that IP address statically assigned, like we're going to do tonight in the lab in a second, meaning you manually type it in your computer, each one of the computers, or is it dynamically assigned through DHCP, the DHCP server. So the next is Reverse Address Resolution Protocol, RARP. The problem is you cannot use ARP. If a device doesn't know its own IP address, the solution is RARP. The client sends a broadcast message with a MAC address. It receives an IP address automatically. RARP server maintains a table, much like Excel, just like the ARP. It contains a MAC address, associated IP addresses. It was originally developed for diskless workstations, and these are called dummy stations. Okay, Sears uses them, JCPenney uses them, a lot of retail uses them. And so you don't have a hard drive, you don't have a USB drive, you don't have a CD-ROM, you don't have even memory in some of them. It's just a chip that's connected to a keyboard, mouse, monitor, and a Cat5 running to the server. That's it. IP version 4. This is what we're working on today and tonight, and most networks are still working on it, even though version 6 is available. It recognizes two addresses in version 4, logical address, which is a network layer, and physical address, which is your MAC address, and hardware addresses of your network. Hardware addresses would be like your switches all have hardware addresses. Your routers have hardware addresses. The IP protocol handles these addresses. Specific parameters has to be at least a 32-bit number, unique 32-bit number, divided into 4 octets like every version 4 IP address is. Example, it's separated by periods, by the way, the 4 octets are. So example is 144.92.43.178. So each one of these separated by periods is an octet. All right, 4 octets. Each octet is 8 bits, or the equivalent 8 bits is 1 byte. All right. So let's talk about classes. Up here on the board, I've written on some stuff that you're going to be using tonight in just a second. The word LAN and a 10.0.2.1, 2.2, 2.3, and a subnet of 255.0.0, and I put class A. The reason I put that is because of this slide here. So class A, the reason you can, the way you determine what class a network is, a LAN is by this diagram here. So class A, the first octet, the 10 dot octet, the first octet, begins with whatever. 1 to 126 is class A. 1 127 is not there because that's used for local loopback. 127.0.0.1. 128 to 191 is Class B. Class C is 192 to 223. Most of your home users use Class C for your Wi-Fi routers. Some of you might use a 178 or 179 or 180, but most of you are going to use a 192, I'm guessing, on most of your routers. But some do use like a 172. And the third column talks about these are the number of networks available in that class. Like in this college at Rock Valley, we, on all the local computers, for the most part, are Class A, a 10 dot number, okay? 10 dot number. 10 dot numbers can only work in local LANs, okay? Can only work in local LANs. They cannot connect to WANs, internet connected type of networks, but only LANs. That's why the number's smaller, by the way. This 1 through 126 octet, Class A, can be used tons of times over and over again like we're going to use tonight. All three of your groups will use the same three pair in your network. The .1, the .1, the .2, .3. All three of you can use it. And that's why it has a lower number. Maximum addressable hosts per network, though, look at that number. 16,777,214. So it's pretty much endless on the different hosts per network that can be attached to a LAN in a Class A. That's why it's used for businesses mainly, small area, small to medium sized, large businesses. Not so much at home because you don't need it. You don't need it at home. At home, you're connected to your Wi-Fi router, which is connected to the internet. That's it. That's your network, right? For the most part. You're not sitting there showing, hey, Joe, can you send me a file from your computer? Yeah, I got it. Okay, you're not doing that. Because you can do that without the internet. You don't need the internet to do that. A LAN can help you connect to one another without the internet. Because before the internet, we did have the network, all right? And that's kind of mind-boggling to some students. But I remember networking, when I first started out, we didn't have internet. We had network, we shared files, we shared data, printed stuff, but we didn't have internet. And so Class A was mainly used when I first started in networking. But Class A, B, and C, there is a Class D, by the way, which we'll learn about when you do the subnet exercise here in a couple of weeks, I think. And it's for broadcasting only. And so, and broadcasting meaning it's reserved for networking to broadcast information, like apps will use. Everybody shut down your computer in 5 minutes. That type of message. That's a Class D, okay, the broadcast message. So Class D, rarely used. It's multicasting, like I said, 224.230. Class E, 240.254, experimental use on that one. 8 bits have 256 combinations. So each octet can have a number in that octet from 1 to 256. Okay, in each octet, each one of the 4 octets. However, because of the nature of the octets, the nature of networking, we only use 1 through 254. We don't use 255, 256. 0 is reserved for a placeholder. 255 is reserved for broadcasting transmission, which we'll talk about in a second. Class A share the same first octet, the network and the network ID. Host is the second through the 4th octet. So in a Class A, number 2, 3, and 4 octet are the host information. Class B, 0 through 15, the first 2 octets. The host is octets 2 and 3. Okay, it would be 2 and 3, it'd be the 2 and 3 on each one. 2 and 1, 2 and 2, 2 and 3. That would be a Class B. If it was a Class B, that's what it would be. Class C share the same 3 octets, and they host through the 4th octet only. And when we do the networking subnet exercise, you'll do an exercise where you'll go through, find a class for all the IP addresses on the sheet, determine what class it's in, what the subnet, what is the network, what is a host for each one of them. It's a pretty easy exercise once you see it and do it. All you need to know now, though, is that networks are subdivided by classes, and those classes some classes allow for more hosts than others. Class A mainly is for local stuff within a room or a building. Class B and C is where you get into connecting to the internet or the WAN when you get into Class B and C. So this is talking about version 6. And the reason version 6 is even here is because, believe it or not, we are eventually going to run out of IP addresses when it comes to web servers and web sites. As you can imagine, people getting websites are more prevalent today, individuals and businesses alike. And so eventually we would run out of IP addresses for those connections. So that's where version 6 came in. It really had nothing to do with local area connections, because we had plenty for that for businesses to internally use. We're talking about websites specifically. Or not just really websites, it could be web apps, it could be APIs, a whole bunch of different things. But each one of them had to have a separate IP address around the world. So this is a screenshot of IP addresses and their classes. Again, all I need you to know on this is notice the red portion. On A, many more hosts can be attached to A, which makes sense because it's a localized environment, and you want more control over that. B and C, you get less and less hosts and more network information, more routing information, So we needed a new schema, though, really for the web, for web connected whatever. You might have heard of a term called Web 2.0 or Internet of Things. You heard of that maybe? IoT, it's a big term. Anybody heard of home automation? Home automation devices to turn on your lights, shades, doorbells, doorknobs, video. All those devices I just mentioned needs an IP address. Security monitoring. Now, that's a big business now. All monitoring through IP, meaning every household that has these security monitoring needs a separate IP address just for that security monitoring a lot of times. So households today, if they have the right connections, could actually have up to 2 to 3 unique IP addresses for that household. And businesses, you're talking anywhere from 8 to 10 to 20 IP addresses unique for that business. And that's just one business and one household. So times the millions and millions and millions of households and businesses, you can see we're starting running out of stuff. And by the way, if you've never bought IoT, Internet of Things, or home automation, I do recommend one. It's fairly reasonable because they can be pretty expensive. I found one actually at Walmart. I saw a demo of this here at the college a few semesters ago, and it's called the Wemo. You ever heard of the Wemo? Wemo is a little white box about the size of this business card that you plug into the wall. Once you plug it into the wall, you connect it to your Wi-Fi. It has a little Wi-Fi access point built into it. It connects to your access point. Then once you connect the access point, then you can buy these devices. We have I think 5 or 6 in the house. What they are is they're light bulbs is what they are. They're light bulbs that basically are controlled by the Wemo device. And so with an app, with this app here, I can right now, I can turn on and off 4 lights in my house from right here with the Wemo. The Wemo, I bought it at Walmart actually. It was on sale for like $20. It was a clearance. They're normally like 50 or 60, but it's not too bad. But you get the Wemo, and I think you get 3 or 4 other devices you can connect to it. That one had the Wemo device, the little white box, and it had 4 or 5 light connections. You basically screw in any light connection in your house, and it would control it. So that's what I recommend. WeMo has a lot of different ones, a lot of different types of devices. It's WEMO, and it's the most reasonable. And if you're wanting to start somewhere, that's probably where you start. Because I know guys that have like automated shades that they can control from anywhere, locks on their door, video on their door, and so tons of different home automations. And it does save, like I control it in the morning and at night when it goes on and off. And when we're gone, I can control it too. So that kind of helps the safety. It's good to, for criminals, if the lights are on and going off and on, look like somebody's home. And so definitely pretty reasonably priced now to where consumers like you and I can afford it. 2-3 years ago we couldn't afford it, but now you can. And Rock Valley College does have, by the way, down in the aviation area, we've got a building totally controlled by these type of devices. The entire building, classroom, offices, everything's controlled remotely. And they have cameras on it and they can actually show people how it works. So WeMo, remember that, good one. IP version 4 has also a local loopback address, which I've talked about earlier already. It's called the home or the local host, 127.0.0.1, and we've done that in here where I think I had you ping that first. It's pinging your NIC card to determine the health. If you get 4 returns, healthy returns, you got a healthy NIC card. If you don't have a healthy NIC card, or healthy configurations might be pooched. So the local loopback test connects to its own machine. Powerful troubleshooting tool. It can be used in all OSs. In Linux, it's ifconfig instead of ipconfig. I think I showed you guys the ipconfig /all. What that does is shows you all connected devices. Like on your machines, what we had like 3 NIC cards, I think, something like that, for most of you. And then the Intel is the one that we use for internet and network connection. The other for Cisco routers and switch configuration. The difference in ipconfig and ifconfig, by the way, is an ipconfig /all. It will give you, on ipconfig /all, it'll give you all the NIC cards. ifconfig /all gives you all the NIC cards, plus it'll give you how long each one of them has been up and running, which is a little different than Windows. So here's the Windows one that you guys saw when we did it, the ipconfig all on Windows XP. It gives you the, in this example here, let's do red, the name of the host, which in this case is the computer itself, student X, the MAC address of the computer, and then the IP, subnet, default gateway, DHCP server, DNS server, plural. When that lease was obtained, this was October 26, 2006. When it expires, October 27, 2006, 24 hours. And then it has in here also a wireless one that's disconnected at this one. It's a Toshiba laptop because it says Toshiba wireless. ifconfig/a instead of all gives a little same information but in different format. So binary and dotted decimal notation. What this means basically is a dot operator in between each one of the octets separates the IP address. The dotted decimal addresses has binary equivalent, converting each to an octet, removing the decimal points, can then take the entire 10.0.2.1 to one long binary IP address. Subnet mask, like this one right here. This is a class A. So if you remember from the chart a few slides back, it said it only uses the first octet for the networking. That's why 2, 3, and 4 are 0. So class B would be a 255.255.0.0. Class C would be a 255.255.255.0. And so, by the way, when you type in, you'll see this time when you guys type in your IP address and hit the tab key, it'll automatically fill in the subnet for you. the default subnet, which is a 255.0.0.0. But a subnet is a 32-bit number. It identifies the subnet of that network that you're working on. So you can have the same IP ranges and different subnets. That's what you can subdivide your network. And that's why Class A, you can reuse those IP ranges over and over again, but have different subnets for each one of those. So what happens is it identifies the device's subnet, combines it with the device's IP address, which is those three there at the top, 1, 2, and 3. It informs the network about the subnet, the network where the device is attached. It's 4 octets, the subnet mask is, expressed in binary or dotted decimal, like here, the dotted decimal. And it's assigned same way as an IP address, either manually or automatically. So the default subnets, Class A there, Class B, and Class C. It just depends on the different 255s you have available or that you get plugged in. Class A is 1, Class B is 2, Class 3 is 3 255s. So subnetting, the big thing about subnetting is it allows you to have a single class into multiple smaller segments, where you can subnet a network to have audio, video, maybe sound, or maybe audio, video, let's say, I don't know, graphics, and you can even go on department level. I've seen it to where subdivide the network by department in the business. Every network, and when they're subdivided, guess what? You can't see what each other is doing in the other segments. They're not allowed. You can't see each other, so it has a level of security as well. So you're never going to collide, but you're also not going to see, which helps. So because in networking, we don't want all employees to see, for example, all the HR files. Not good, especially the ones that says promotions or something like that, or evaluations. People will be wanting to get into those all day, right? Maybe I'm just the only one who would do that. But you know what I'm saying? Subnetting helps with security, helps with managing a network, controlling traffic. Non-subnetted networks use a default, like up here. This will be like we're going to do tonight. It's a non-subnetted. We're using the default, 255.0.0.0. Okay, I'm going to slip ahead to the DHCP. So the DHCP, what it does is it borrows or leases an IP address temporarily for you. But because of the ARP table, it can stay longer than that 48 hours or whatever the lease might be. And the DCP service, as a lease, you can, by the way, initiate a new lease automatically with the right command. You can do a release all, release IP, and it'll release your current one and give you a new one. But here's what happens. Client A asks what IP address can I use? Hi, Client A, use 123456789 as your IP address from the DHCP server. Number 3, Client A takes it. I'll use it. Client, or number 4, the IP address 123456789 is now assigned to Client A. And it would go through and do it on every one of the machines, just like that. No, they don't actually talk, but it happens really quick. All right, and it keeps it assigned. By the way, once that's all done, the DHCP does its job, then the ARP table adds it to its table, that information. Expiration can be automatic, manually. The manual one can be done by the client side if you know the commands to use, or the server side. Circumstances requiring lease termination is where DHCP fails and server fails and is replaced totally. Windows releases a TCPIP setting. DHCP services run on several server types. mainly Windows though, but there is open source DHCPs for Linux and Macs. But for the most part, in most businesses, Windows is going to be the default DHCP server. There are some businesses though that do run only Linux and only Mac, and they also have their own network operating systems to run DHCP. So the differences mainly between IP version 4 and version 6 is, let's look at the version 6 local loopback. There it is. 0.0.0.0.0.0.0.1, separated by semicolon or colon. And then abbreviated loopback is : 1. Much different than IP version 4. The scope of IP version 4 can reflect the scope of the transmission recipient. It can have what's called a unicast address, representing a single device. It can have a multicast address, representing multiple interfaces, often multiple devices. On the scope of IP version 6, Anycast can address any one interface from a group of interfaces, and anyone can accept transmission. The format of version 6, beginning of address, a variable length field, indicates the address type, whether it's unicast, multicast, anycast. And one of the things I didn't mention in the book, but one of the powerful things about version 6 is we'll be able to subdivide the network globally to where we can actually have our own, the military can have its own subdivided network exclusively for military and governmental usage that will not be used, that cannot be used by anyone else. If it is used, it can be found out easily by being traced. Also, they're talking about doing the same with medical and emergency folks as well, being able to do that. And that would be with the Anycast, because you can have multiple different protocols and different variances that you can use. It's kind of like if you ever, I don't know, when I grew up, I used to play around with it. I don't know if anybody here ever did. Everybody play around with a shortwave radio or ham radio or a CB radio when you were a kid or growing up and knew somebody that did. And they had different channels you could go on. You weren't allowed to go on some channels. And if you did go on those channels, they told you to get off, right? And so, like, every once in a while, I'd switch to, like, say, the Highway Patrol had a certain channel. I like listening to it sometimes. And it was fine unless you made a noise or tried to do something. They could tell. They'd say, whoever's on this channel, get off. We're getting ready to go into whatever mode. And, you just, Highway Patrol tells you to do that. Okay, I'm going to flip the channel off to something else. Because evidently, if you were on it long enough and you didn't get off, with triangulation, even back then, they could find you eventually. And so I wasn't going to do that. But anyway, the reason I mentioned that was that even with version 6, there'll be the hackers and people will try to penetrate it for sure. Maybe will they be successful? I don't know. Probably so eventually. But it's going to be much easier to trace it with IP version 6 than it was way back when, like on the CB radio days. It took a little bit more to find it, and it wasn't like pinpointed. I'll end on this one before we go to our lab. Host names and DNS. How many have a website, or you've worked on a website, or your business does that you work with maybe has their own website? No? Well, when websites are created, they have a domain name, like abc.com, right? Well, those, they don't have a number that they give people. They give people the name, abc.com. But every business does have a number, which is a TCPIP IP address that the ISP gives them. So, for instance, if you get a web host through GoDaddy, they're going to tell you, okay, here's your IP address for your website. And you can use that IP address to FTP up your stuff, upload your files, and that's your IP address. It's like it's your phone number, your physical address at home, or your social security number. But people remember words, computers remember numbers. That's where DNS comes in. Because the domain name system converts the name to the number and the number to the name, basically, is what its job is. And you'll actually see when you do an IP config all, DNS is one of the numbers in there. DNS is a network service that does just that. it translates every website you go to, internally and externally, to a number, to an IP address. And then vice versa, it can translate a number into a name. Host is the internet device in host name and DNS. Host name would be the name describing the device, like abc.com. Domain names, you're familiar with these already. Websites, group of computers belonging to the same organization, though, can also be a domain name, like RVC is a domain name. RVCnet is a domain name here at Rock Valley. But like local loc.gov, rockford.gov, that's a domain name as well. Associated with a company university, rockvalleycollege.edu. A fully qualified name would be like jasmine.loc.gov or say rockford.il.gov. That would be an example. And all the municipalities in Illinois, by the way, have the same type of acronym for their municipalities. Fully qualified is local host name plus a domain name. And then the domain names, lastly, it's a character string separated by dots, represents the level in that domain hierarchy. So an example would be a .com, a google.com. If you've ever bought domains, .coms are more expensive than, say, the one we used for our quiz earlier, .it. That's not that expensive. .info is not that expensive. Top tier, top level would be like a .com, a .gov, a .edu, a .org. Those are all top tier. Second level would be the name of the domain, like Google or Rock Valley College. Third level is the domain www. Second level, many contain third level subdomains, things of that nature. But what recognizes and keeps track of all this is what's called the ICANN. All right, so I'm going to stop that.